Hey guys, it's me. I am not here today, as you can see, so I'm going to be talking to you through a video. This is going to take about 15 minutes, so it shouldn't take all class period. I'm at home doing this. You can hear my clock binging in the background. So what have we been doing? We started out with gas laws. We did 2 CAS laws, and then we moved on and did our brochure assessment. Hopefully everybody's turned that in today, as well as turning in a hard copy, as well as turning in to Turnitin.com. If you didn't turn it in to Turnitin.com, I'm going to give you a 0, so even if you turn it in late, turn it in. Okay? So moving forward, we're going to talk about the gas laws. Boyle's, Charles, we've already talked about. We're going to talk about the Gay-Lussac's and the combined gas law today, but as you can see, we still have Avogadro's, Graham's, the ideal gas law, and actually our gas stoichiometry still to talk about. So let's move forward. Alright, so we've talked about Boyle's law. Where have we been? We talked about Boyle's law, that this is an inverse relationship. So this is the graph where you get the hyperbola, and we get P and V and P2, V2. Most people got this, okay? So moving forward, we talked about Charles's law, and this involves volume and temperature. And this is a direct relationship, so as volume increases, the temperature decreases. And as the volume increases, the temperature increases. So they are a direct relationship. This is linear, okay? We've also done triple point experiment. You will have to read a graph like this for your final assessment at the end of the unit, which I think is March 31st. So you need to, if you do not understand, and some of you did not get these problems correct when you had to read the graph, you couldn't tell me what state of matter it was, or you couldn't explain to me what a triple point, what the critical point was, you need to go back and refresh your memory. Google it. It's out there. There's YouTube videos that will explain it all too. There's ones on our, well, we put it linked on our website, so please go use those tools to refresh your memory. So I want you to get out your warm-up sheet, and you're going to do this warm-up. Okay, a 1,000-liter container is filled with air having a pressure of 101.3 kPa. The air is pumped into a second container, and the new air pressure is 40.00 kPa. What is the volume of the second container? So stop this video, get out your warm-up sheet, also get out your gas law guide, okay, and get those things out so you can do this warm-up. On your warm-up, you're going to list your givens. You're going to write down what gas law equation you used. You're going to rearrange the gas law, solving for the unknown variable. You're going to plug in your givens and solve for that unknown. So now stop the video, and I want you to compare your answer with your neighbor and work through it collaboratively. Okay, first do it individually and then compare answers. If you guys don't get the same answer, then figure out who went wrong and please help them work through it. Okay, so this is important that everybody understand. So stop the video now and continue working on that, and then come back. Okay, so I guess you're back. Alright, so we're going to talk about Gay-Lussac's law. The ratio of the pressure and the temperature of a gas is constant at constant volume. So this involves pressure and temperature. Now I want you to think back in your memory banks to when we did the gas law demos, when we did all those demos, and this is actually the demo you did where you increased the pressure, and as you increased the pressure, the temperature went up. See if you can recall what that was. I'm just not going to tell you what it is. I want you to think back about it, okay? So think back in your memory banks to those demos and see if you can figure out when that happened. All right. So Gay-Lussac's law is also a linear relationship. So write this on your gas law guide. Write down what the shape of the graph is. The graph is for pressure and temperature is a direct relationship. Therefore, if pressure goes up, the temperature goes up, or as the pressure goes down, the temperature goes down. And look at temperatures in Kelvin. Everything has to be in Kelvin. Now, pressure can be different. It can be at ATM and so on and so forth, but as long as everything matches, okay, that's what we're looking for. But temperature in these problems, all gas law problems, has to be in Kelvin. And so if you are given your problems in Celsius, you need to add 273 to get it to Kelvin. So Gay-Lussac's law says since the ratio of a pressure and temperature of a gas is constant at constant volume, it remains the same at different temperatures, at different times, excuse me. So we have pressure and temperature at time 1, and we have pressure and temperature at time 2. So we have P1 over T1 is equal to P2 over T2. Here's a problem that's on your paper. A rigid container having a volume of 10 liters is filled with hydrogen gas at 200 Kelvin and 100 pascals. The hydrogen is cooled to 20 Kelvin. What is the final pressure? Let's walk through this problem together. First you decide what the problem is. Now remember, I am telling you what the problems are right now. You're going to get to a worksheet called Gas Law Galore, and I'm not going to tell you which gas laws they are, and you have to be able, based on the givens, decide which gas law you will be needing to use. All right, in this one, since the initial pressure and initial temperature and final temperature are given, the final pressure is unknown, this must be a Gay-Lussac's problem. There's our Gay-Lussac's equation. And I'm going to rearrange it to solve for the unknown variable, which is P2. There we go. And then I'm going to plug in my equations. Look, they show all their units too, and we can see that Kelvin's going to drop out, and I'm going to end up with a pressure of 10.0 pascals, 3 significant figures. If I wrote that in scientific notation, it would be 1.00 times 10 to the first pascals. All right, so there's another problem on your paper. I want you to go ahead and try that one by yourself. All right, a rigid container having a volume of 13.0 liters is filled with hydrogen gas at 225 Kelvin and 110 pascals. The hydrogen gas is cooled to 35.5 Kelvin. What is the final pressure? Stop it now, work the problem, and then come back and compare it to mine and see how you did. Okay, so you must be back. Here's what I did. Here's my givens. Look at, I listed all my givens with their units. How lovely. And there's my equation. P1 over V1 is P2 over V2. I've rearranged it to solve for my unknown variable. I plugged in my units, plugged in my numbers with my units. And look, I can see right off the bat when I look at that, 110 is only 2 significant figures. So my final answer can only contain 2 significant figures, which is 17 pascals, or if I rewrite it in scientific notation, which you guys all need to do, you will get 1.7 times 10 to the first pascals. So, I want you to try a warm-up. On your warm-up sheets, I want you to do this, and then stop, collaborate with your neighbor, compare the answer, make sure you guys get the same one. This time you're solving for T2, so you have to rearrange this algebraically. Collaborate with your neighbor. Also, I'm giving you a hint. Temperature here is given to you in Celsius. You need to convert this to Kelvin by adding 273. Do you need to memorize that? Absolutely not. It's written on the back of your reference sheet, which you guys all will get on your test. So please use your reference sheets. Now moving on to combined gas law. The combined gas law is also on your reference sheet. You don't need to memorize it. Okay, you just have to recognize when you're going to use it based on your givens. And this says that the ratio of a product of pressure and volume to the temperature of a gas is constant. Okay, so we can again do this at 2 different times, time interval T1 and T2. Now, if you look at your gas law guide, it's a little trickier. That's why I'm going through with these ones with you. All right, it says on your paper, if a volume of a gas doubles and the temperature of a gas quadruples, what must happen to the pressure? Now, don't freak out. I know you guys are looking at this going, whoa, 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 there are no numbers. What am I supposed to do? Sorry, guys, you heard a dog barking in the background. That was my dog. I had to go let him out because there were ducks in our pool, and he had to go chase them away. So, all's good now. I'm back. So, I was saying that you don't have to stress over these problems, the fact that there's no numbers in them. We're going to use the combined gas law, and I'm going to show you how to solve for these. Here's a written solution. Now, this is what freaks everybody else when they see this written solution. It says, if the volume doubles at constant temperature, then the pressure halves. If the temperature quadruples at constant volume, then the pressure quadruples. If the pressure halves and then the quadruples, the final pressure is double the initial pressure. Don't worry about these words, okay? I'm going to show you a really easy way to do this. What you have to do is you have to write the equation P1 V1 T1 all is equal to P2 V2, and assume that all the P1s, the V1s, and the T1s equal 1. Okay, then you just follow what the word says. Okay, so here we go. P1 times V1 over T1 is equal to P2 times V2 over T2. Now I want you to assume that P1, V1, and T1 are all 1. And now, P2, now if you look back and look at it, it says, what must happen to the pressure? So that is what we're solving for. So P2 is a question mark. Now V2, I got that 2 from, it says, if the volume of the gas doubles. So it went up by a factor of 2. So I made V2 equal to 2. And temperature says, and the temperature of the gas quadruples. So that goes up by a factor of 4. All right, so I put a 4 in there. Now you're just solving for it. So I'm solving for P2. I'm rearranging my equation. P1 V1 T2 is equal to T1 over V2, or T1 times V2, sorry. So P2 is equal to, now I'm just plugging. You don't even have to worry about units on this one. Isn't that nice? I would never grade you down. Okay, so you have 1 for, P1 is 1, V1 is 1, T2 is 4, T1 is 1, and V2 is 2. And I solve for P2, and P2 is equal to 2. Therefore, the pressure doubled. That's all you have to say. The pressure doubled. Okay, so you have another one on there. You have 2 more to practice with, actually, number 12 and number 13 on your gas law guide. I want you to try doing them. All right, stop the video. Assume all P1s, V1s, and T1s are 1, and then plug in what you think P2, V2, and T2 are, and then solve for the unknown, and then come back and let's see what happens. All right, I will work through them with you, but I want you to work on them. All right, try to work through them. So stop the video and try them, and then come back and compare them to mine. All right, so there's the 2 problems. If the pressure of the gas halves and the temperature doubles, what happens to the volume? If the pressure of a gas doubles and the volume triples, what must happen to the temperature? So the first one, number 12. I assume that P1, V1, and T1 are all 1. All right, I am solving for V2, so I rearranged it. Okay, and I said, oh, P2 is a half, because it states right there the pressure halves. And the temperature doubles, so I put 2 for the T2, and I plugged them in, and then got V2 is equal to 4. So that means the V2 is 4. That means the volume quadrupled. Okay, so for number 13, I didn't go through and work it through you, but the answer I got for number 13 was T2 is equal to 6. Therefore, the temperature increases by a factor of 6. I don't know what the number, how you would say 6, you know, it's not equivalent to like quadruple, so I would say increases by a factor of 6. All right, so practice tonight is the Gay-Lussac's Law and Avogadro's Law practice worksheet. You're not doing the Avogadro's Law practice problems. You're only doing 1 through 4, which is the Gay-Lussac's problems, 1 through 4. Please practice those tonight and check your answers with the key. In addition, there's a video online. I want you to watch that video. Okay, it's on how to get all the gas laws from the ideal gas law, which is called PV equals nRT. I want you to take notes on this. The notes are homework. Okay, the notes are homework. And that will be turned in on Tuesday when I return. You guys have a great day, and I will see you all tomorrow. Bye.